AI is transforming our world into a smart world. When I say smart world, it includes everything, digital home, smart retail, to intelligent factory. AI is automating everything. AI is trying to assist humans in every possible way. But at the same time, in some ways, AI will also replace the humans. You think of transportation. Transportation, ADAS to autonomous vehicles. AI is automating everything. Eventually, AI might replace the drivers. Beyond the geopolitical situation between United States and China, the world is looking at how to balance the semiconductor supply chain. Why? Because during COVID, the supply chain was disrupted. Coronavirus originated from China, helped us to realize it's important for us to balance the semiconductor supply chain, isn't it? Now, every ambitious country like India wants to be part of this incredible journey. How best we can build the manufacturing ecosystem. Like Japan, Korea, Taiwan partnered with United States in 70s and 80s during the evolution of semiconductor industry. I believe that to train AI systems like ChatGPT, large language models, we need cloud infrastructure or vast data centers built with advanced AI chips. So obviously, it demands domain-specific CPUs, GPUs, and accelerators. So it creates the new opportunities for the growth of semiconductor industry. So we would be looking at how to design advanced AI chips using domain-specific processors. At the same time, we also need to look at the possibilities, architectural improvements, all kinds of processor you can think of dealing with one ISA. You don't understand this, then you can think of UVM, the best example, how you are enjoying the methodology UVM. It used to be like we had to deal with the different languages, C, C++, Vera, E, and then for language E, we had to deal with Specman, and we had different methodologies like OVM, VMM, AVM. Then later on, what happened? Everything got merged, and then it became like UVM, Universal Verification Methodology, IEEE standard. And that's based on System Verilog IEEE standard. So in this case, we might need to configure the USB VIP as host, and then we might want to check like how the communication is going to happen between USB and memory. But that's going to be decided by CPU, so there will be firmware C test case. So usually we compile the C test case into object code, binary code, and we load that binary into memory. Then the CPU will read that, and based on that, it's going to initiate the operation between the interfaces, right?
So after that morning session with the keynotes and the good panel discussion that we had, we continue into the afternoon session, into journeying beyond AI, unleashing the art of verification. The speaker is Sivakumar P R. He is the founder and CEO of Maven Silicon. He is responsible for the company's vision, overall strategy, business, and technology. He is also the founder and CEO of ASIC Design Technologies. Sivakumar is a seasoned engineering professional who has worked in various fields, including electrical engineering, academia, and semiconductors for over 25 years. In the semiconductor industry, he has worked as a verification consultant for the top EDA companies, Siemens EDA, Cadence, and Synopsys, and helped various ASIC and FPGA design houses deploy and use various verification methodologies effectively, resulting in successful tape-outs of IPs, chips, and SoCs. He now specializes in offering verification IPs and consulting services and EDA flow development, and has delivered corporate training courses for the top EDA and VLSI MNCs. He is also the author of our online VLSI courses and blogger for design and reuse, SemiWiki, and RISC-V blogs. Sivakumar is the recipient of the Outstanding Technical Achievement Award from the Cadence Design Systems and Silicon India magazine recognized him under the top 10 most promising CEOs in India, 2023. He holds a degree in electrical and electronics engineering from the Madurai Kamaraj University, and the LinkedIn profile is given here. So please join me in welcoming Siva to the stage.
Good afternoon, everyone. Hope you are enjoying all the keynote sessions and discussions. In this session, I want to take you through the incredible journey of exploring the art of verification. That's why I titled it as Journeying Beyond AI. Are you ready for this exciting journey? Post-lunch? Right. Good. About Maven Silicon, we have been well known for our VLSI training services as a top-class VLSI training company for more than 14 years. In this journey, we emerged as an approved training partner for the organizations like RISC-V, ARM, mainly to upskill the engineers like you on various processor architectures. We also collaborate with Tier 1 VLSI companies and startups to upskill their engineers on chip design. You consider chip design, we train engineers in various domains like digital design, design verification, DV, DFT, and physical design. Actually, we started our journey in the B2C space primarily to upskill NCGs on chip design. And in this incredible journey, we deployed more than 5,000 VLSI engineers in the semiconductor industry. I am very proud about this achievement. I really want to be thankful to all our employees. We have more than 100 employees working with Maven. We provide various kinds of corporate VLSI training courses for people like you. You want to learn anything about ARM architecture, we provide various kinds of courses specific to ARM. You want to explore what is RISC-V, you want to know everything about RISC-V, we provide various courses for RISC-V. We also provide different kinds of learning paths. That's more about offering online training solutions. You consider the learning paths, there could be various things like digital design, design verification, DFT, and physical design. And for the experienced engineers, we provide various kinds of VLSI programs and some protocol-specific courses too. Synopsys and Siemens EDA, they are our EDA partners. We work for Tier 1 companies like Qualcomm, Samsung, and many more customers. That's about Maven Silicon. Everyone is talking about AI, whether you like it or not, artificial intelligence. AI is transforming our world into a smart world. When I say smart world, it includes everything, digital home, smart retail, to intelligent factory. AI is automating everything. AI is trying to assist humans in every possible way. But at the same time, in some ways, AI will also replace the humans. You think of transportation, ADAS to autonomous vehicles. AI is automating everything. Eventually, AI might replace the drivers. Same thing might happen to us also. Semiconductor industry is not exceptional. We are looking at how to use AI everywhere, artificial intelligence. So it's going to be like AI-driven EDA to AI-driven chip design to AI-driven fabrication. Then in many possible ways, AI will assist engineers like you, but in some ways, AI will compete with you. If you are the engineer who focuses on specific things like debugging simulation failures or writing test cases, you like it or not, you might be competing with AI at some point of time. That's where I'm here to show you the big picture, the art of verification, why it's something important for you. It's time for you to understand the big picture, the art of verification so that you will be able to enjoy this journey, journeying beyond AI. That's what's important for engineers like us. What's happening in our industry? It's going to be like AI-driven semiconductor industry. Let's look at our ecosystem, semiconductor ecosystem. When I say ecosystem, what comes to your mind? Probably it could be semiconductor supply chain. Why I want to talk about semiconductor supply chain, I tell you the reason. Recently, I bought the book, Chip War, written by Chris Miller. How many of you have read the book? Anyone here? Good, that's an amazing book. You will understand everything about semiconductors, how we invented the IC. Great people like Robert Noyce, how they invented IC, and the evolution of semiconductor industry. That was great. But when I was going through the book, I didn't see India anywhere. India was missing the world map. That's what I'm going to show here. We contribute so much for the growth of global semiconductor industry, and we are well known for our design expertise, especially for design verification and physical design. That's what I'm going to explain today. You think of semiconductor supply chain. Beyond the geopolitical situation between United States and China, the world is looking at how to balance the semiconductor supply chain. Why? Because during COVID, the supply chain was disrupted. Coronavirus originated from China, helped us to realize it's important for us to balance the semiconductor supply chain, isn't it? Now, every ambitious country like India wants to be part of this incredible journey. How best we can build the manufacturing ecosystem. Like Japan, Korea, Taiwan partnered with United States in 70s and 80s during the evolution of semiconductor industry. You should be aware of it. So my message to the world, my message to you, the contribution from every brilliant engineer from every country is significant for the growth of global semiconductor industry. Like how Bob Noyce invented the IC in the United States, and then how Maurice Chang built the semiconductor ecosystem in Taiwan. That's what's going to happen now. You want to understand the supply chain, it's very complex. I want to explain this because I want to show you that India is there. We have an army of engineers. We are well known for our design expertise, especially in design verification and physical design, right? So we are there. Let me explain how this supply chain works. You think of OEM, Apple, how it makes MacBook. It designs a complex chip, SoC, called M-series chips. Have you heard of it? M1 series, M2 series. First time, Apple introduced the concept like how one can use a RISC processor even for PCs and laptops. How they make this chip? They buy IPs from various fabless IP and chip makers from various countries. The primary component could be processor, ARM processor. ARM is based out of UK. They might be using various kinds of interface IPs. For example, if they are using USB IP, it could be from even Synopsys also, it might be, then that development might be happening in India, right? You consider almost all these tier one product companies, VLSI product companies, they have R&D center in India, right? So they buy all these IPs from various fabless IP companies and chip makers from various countries. And then they send the design to TSMC, based out of Taiwan. TSMC fabricates their chip. To fabricate the chip, TSMC buys wafers and gases from countries like Japan. And then they also use lithography machines from companies like ASML. ASML is based out of Netherlands. And TSMC fabricates the chip. Then finally, the chip goes to Malaysia, countries like Malaysia, for the assembly and testing. And then the final product is assembled in China. So every country contributes to the growth of global semiconductor industry. And in India, what I can say is more than 20,000 engineers, they actively work on various kinds of chips. So we have good presence, and it's time for us to think more about building a good semiconductor manufacturing ecosystem. Let's look at how our industry is evolving. It's going to be like AI-driven semiconductor industry. I'm trying to visualize this way. We all need to have the ability of visualizing things. We are all DV folks. We have to be creative. If I think of AI, I believe that to train AI systems like ChatGPT, large language models, we need cloud infrastructure or vast data centers built with advanced AI chips. So obviously, it demands domain-specific CPUs, GPUs, and accelerators. So it creates the new opportunities for the growth of semiconductor industry. So we would be looking at how to design advanced AI chips using domain-specific processors. At the same time, we also need to look at the possibilities, architectural improvements. Whatever we have been doing all these years, it might not be possible for the next generation of AI chips. So we are looking at like how to integrate the neural engines with memory, the efficient data transfer with respect to dealing with memory. That's highly needed for advanced AI chips. So that's where we are looking at the options like using chiplets or 2.5D or 3D packaging options. So things are going to change with respect to the way we design the chip. The more and more we learn, the more and more we produce advanced AI chips, that's going to accelerate the evolution of AI. In parallel, EDA folks, they are also looking at ambitiously like how to use AI everywhere. It's going to be like AI-driven EDA, whatever you want to do, whether it is design verification or DFT or physical design, they will look at like how to use AI efficiently for everything. That will also create new opportunities for EDA. They would be providing solutions like EDA in the cloud. Or if their customers, they are going to design very complex chips, then obviously they would be looking at buying more emulators or new solutions. This is how it's going to accelerate the growth of AI. It's cyclical. This is going to continue. And once the AI becomes stable, it's going to have huge impact on everything, smart world, transportation, or other things like communication, cloud, and healthcare. That's how it's going to evolve further. Now let's look at the system-level design. This is something important for the DB engineers like you. It's time for you to understand the system-level design, how things are changing. One good example is Apple is looking at, or I would say like Apple is using ARM processor for their MacBook. That is something new. These chips are very complex. They have M-series chips, M1 series and M2 series. The complexity ranges from 16 billion transistors to 100 billion transistors. But the real problem is OEMs like Apple, they will have to deal with different kinds of processors when it comes to building this kind of complex SoC. They have to deal with different CPUs, GPUs, accelerators. The challenge is each processor is based on a specific ISA, instruction set architecture. That's where I'm trying to explain to you why it's something important for you to understand the system level design, right? So each processor is based on specific ISA, and each processor comes along with unique stack, software stack. That's going to be very challenging. That's where RISC-V is trying to help us. RISC-V is an open ISA. Generally, general purpose ISAs, they last for decades. x86 has been there for more than 40 years. That's good, but if you consider special purpose ISAs, they will not last for more than decades. So that's where we engineers are looking at how to use RISC-V efficiently to build complex chips like M-series chips. So it's going to be for CPU, you can think of using RISC-V. For GPU, same ISA, you can think of using it. Even for DSP processors, or image processors, or AI accelerators, or neural engine. For all kinds of processor, you can think of dealing with one ISA. You don't understand this, then you can think of UVM, the best example, how you are enjoying the methodology UVM. It used to be we had to deal with the different languages, C, C++, Vera, E, and then for language E, we had to deal with Specman, and we had different methodologies like OVM, VMM, AVM. Then later on, what happened? Everything got merged, and then it became like UVM, Universal Verification Methodology, IEEE standard. And that's based on System Verilog IEEE standard. And that has made our life so easy. Standard is very important, right? That's how RISC-V is going to emerge. RISC-V will emerge as an industry standard ISA for all computing devices. It's going to be a powerful ISA. The market is growing. So you may need to understand at least one ISA, whether it could be ARM or RISC-V. RISC-V ISA is very simple. It has 40 instructions. You can implement any kind of design with 38 instructions. The base itself can be used to realize any kind of accelerators. You can visualize this way. The architecture is very simple. It's called load-store architecture. What it means is the instruction will be loaded in terms of binary machine language in the memory. The processor is going to fetch the instruction, and then it does the calculation, and then it's going to store the values back into memory. That's why it's called load store. You can visualize this way. And using the privileged architecture, you can realize any kind of processors, from embedded controllers to cloud servers. All right? So we have been discussing about the system level design. Now let's look at the verification. If you have the question, is verification is so important? Yes, it's important because it's very expensive. Next to software, verification is more expensive. You can look at this. Then how the DV folks deal with FPGA and ASIC. One important thing is both FPGA and ASIC, DV folks spend more than 40% of their time on debug. That is one potential area for the EDA folks. They can think of using machine language to improve the efficiency, right? And in terms of languages, PHDL is pretty much used, more than 50%, and Verilog only 30%, and System Verilog is very limited, 30%. But you should be aware, there are some methodologies like Universal VHDL verification methodology. Are you aware of it? It's for the FPGA designers. ASIC world, as I mentioned, DV folks spend more time on debug, more than 47%. And in terms of methodology, 60% constrained random coverage-driven verification, 70% code and functional coverage, and SV is very popular for verification, SVA for assertions, and UPF for power intent. You should be aware of it. I would suggest you to refer the blog, Siemens EDA blog. Very useful. You can understand the trends. Now let's explore the art of verification. I have only 8 minutes more. I will take you through some case studies, like how we build Bluetooth verification IP. This is how the Bluetooth stack looks like. It has application layer, host, controller interface, and controller. So in this case, I'm trying to verify the link layer RTL. When you look at something like this stack, you should be able to visualize how you can model it like verification environment. Here, you can think of modeling the host. You can think of modeling the host as test bench. The test bench can be like host, and then eventually the test bench can configure the RTL. The RTL can be configured something like transmitter or receiver, right? So that's one thing important, how you visualize. At the same time, how you are planning to implement the interface. You have the option like TLM. So here the spec itself defines HCI, host controller interface. You can define the interface directly using TLM. Here you can look at the test bench is acting like host, and we created the reference model in UVM, and we did back-to-back verification. That was the challenge. When you do back-to-back verification, you think about it like how you are going to find the bugs. It might not be efficient. So that's where what I did. I created 2 different teams, one for test bench, the other one for model. And then I asked them to deal with specification. I wanted to find out whether there could be any difference with respect to their interpretation. You have to approach it like this, right? So strategy is important. If you are going to replace any functional model by RTL, then how it is going to happen? You can't ask the engineer to modify the source code. It should be easy, straightforward. That's where you can think of implementing adapters. You look at the right side. Able adapter that converts the DUT interface to HCI. In the real world, designers use interfaces like SPI or USB for the serial communication, and that's where you need to provide this kind of option, right? That's one example, how you can approach. Also, you have to think like how to mimic the real-time environment. If it is going to be like multi-master, multi-slave kind of environment, then how you can simulate it. That's where you can think of using object-oriented programming efficiently, right? You can create these devices dynamically. You can delete them dynamically during simulation. And then when it comes to offering verification IP, you have to look at everything like providing a proper plan, and then test library with test suite, reference models, test bench infrastructure, assertion IP, and the run scripts. This is about processor verification. It's completely different. It's not a wireless component, it's a processor. So here, how we created the environment. We created agents for various interfaces, like reset agent, interrupt agent, and instruction agent for instruction memory, data agent for data memory. So memories have been modeled as slave agents. The RTL uses AHB interface. One thing that I want to mention here is we used a RAL backdoor access to sample the registers. If you think of any processor, there will be so many registers, general purpose registers and special registers. In the case of RISC-V, CSRs, right? So you can think of using RAL to sample the registers. efficiently. And that's how you would be able to generate expected values for the scoreboard. Right? So that's one example how you can approach. Open hardware uses Google's random instruction generator that is very powerful. It does exhaustive verification even with respect to virtual memory management. I defined this flow to verify a RISC processor, not only for RISC processor, you can use it for even any other processor also. The idea is actually designers write the assertions, they embed the assertions in the RTL, they use formal verification to verify all the blocks. You consider a processor, it is going to have standard components like arithmetic logic unit or program counter or decoders, memories. What about verifying each block exhaustively using formal verification? And then you can think of creating a pre-verified design library. It's going to have all the components. Then you give it to the IP-level designers, they can think of creating any kind of processor. Like it could be 3-stage pipeline, 5-stage pipeline, it could be even dynamic pipeline stages. And then for the IP level, verification engineers can think of using UVM to verify the functionality. And to make sure that the operating system works fine on the IP, you can think of using FPGA prototyping. When it comes to subsystem verification, the focus would be more on verifying the bridges and some controllers, system controllers. So mostly it would be more of like using various kinds of verification IPs. And then we would look at like how to generate stimulus to verify the data flow and to measure the performance. That's how subsystem level verification mostly happens. When it comes to SoC verification, the environment is going to be hybrid, mostly UVM components. There could be some legacy test bench components. You might get some legacy test bench components in Verilog or VHDL, then you might want to look at like how to write some kind of wrappers, UVM wrappers, efficiently. There are ways. You don't really need to implement the BFM again in UVM, right? Still, the legacy test bench component is going to be there. You can write some wrappers and you can use it smartly for the SoC level verification. So usually how it happens, it's going to be like directed scenario. Mostly we use C test cases. So before running any simulation, basically we need to configure the VIPs. So in this case, we might need to configure the USB VIP as host, and then we might want to check like how the communication is going to happen between USB and memory. But that's going to be decided by CPU, so there will be firmware C test case. So usually we compile the C test case into object code, binary code, and we load that binary into memory. Then the CPU will read that, and based on that, it's going to initiate the operation between the interfaces, right? And once the data gets transferred, then we need to check the status. So that's where we can think of using RAL to sample the registers. And then finally, we can go ahead and verify the data. This is how the simulation is going to happen. Mostly, it's going to be like directed test scenario. This is one example, right? How you can visualize system level verification. Of course, PSS is evolving. Portable stimulus standard or portable test stimulus standard. It's there. Verification engineers can think of defining scenarios in PSS, and EDA tools are there. It can convert your PSS specification into the test case. If you are planning to use formal verification, it will generate assertions. Or if you are planning to use dynamic simulation, it will generate UVM test cases. That's how it's evolving. ML in EDA improves the performance. We have seen how the industry is evolving. It's going to be like AI-driven semiconductor industry. And AI is used everywhere. You consider DV, test cases, simulation performance are with respect to finding bugs and coverage closure. So DV folks will drive the correct by construction chip design process with an automated physical design flow and emerge as chip architects. So I'm giving you hope, right? So if you think like architect, if you try to understand the art of verification, you will have a great future. So my message is, let's design AI chips. We DV folks will own the design. We will own the verification. Let's design AI chips and let AI implement its AI chips. So AI will take care of physical implementation and we will take care of front-end design. That's my message. Thank you.